is the titration of a weak acid with a strong base. And the titration curve will look a little bit different. We're starting at a higher pH. There's a more gradual slope in this region or actually more extreme slope in this region than here. Okay. The equivalence point, though, interestingly, occurs at the same volume of base added. It will occur at a different pH, however. Okay. And that's going to be the pH that the equivalence point will occur at for the weak acid is going to be dependent on the weak acid itself. And then beyond the equivalence point, we just reach high pH values, and that looks the same for whether it's a weak acid titration or a strong acid titration. Okay, so this is kind of the summary there. And then I believe last time we talked about why the pH is greater than 7 for a weak acid strong base titration. And so when we titrate a weak acid with a strong base, what we are doing is we're reacting all of our weak acid HA with hydroxide. Everything's aqueous, but I'm leaving it off, except for water, of course, liquid, plus A minus. So we've completely reacted HA with OH minus. We're left with essentially 0 on the reactant side if we do a reaction table. And we're left with some amount of A minus. And so we're going to be worried about the equilibrium of A minus with water at the equivalence point. And as we know, this will be in equilibrium with its conjugate acid and OH minus. And because of the presence of this OH minus, the pH is going to be basic. Okay. And so why is the volume at the equivalence point the same? They are stoichiometric equivalents. As long as we have monoprotic acid, okay, one HA will react with one OH minus, or one H plus from a strong acid will react with one OH minus. All right. I think we did this slide where we looked at the different points along the titration curve, and we stated what was going to be present in solution. Did we do this slide? Do you guys have this? Yeah. Okay, cool. So the volume changes very little around the equivalence point for a very sharp change in pH. So once you get a tiny bit past that equivalence point, the pH is changing drastically, and it's only dependent on OH minus. All right, so then let's look at an example. We're going to look at the titration of formic acid, which we could call HF or HA, since both of those are nice and easy to write. We're going to titrate HF with 0.1 molar sodium hydroxide. And we have a Ka value here, 1.8 times 10 to the minus 4. And we're going to look at the pH along the titration curve before any before any base is added, after some amount of base is added, at the equivalence point, and then after the equivalence point. But if you notice question 3, it says, what is the pH at the equivalence point? We don't know, given the information in the problem right now, without calculation, where the equivalence point is going to occur in terms of volume of NaOH. So what I recommend is, if you have a problem like this, that's the first thing you should calculate. So at what volume does the equivalence point occur? Okay. And we know that at the equivalence point, all of the HF is going to be reacted with OH minus to form water and F minus. Okay? So we've done a stoichiometric equivalent of reactants, HF and OH minus 1-to-1, which means we've added the same number of moles of HF, we've got the same number of moles of OH minus as there were initially of HF. So if we find the number of moles of formic acid, we'll take the concentration 0.1 molar. Formol is another unit of concentration, but that's not for us. Moles per liter. And we have 25 milliliters, 0.025 liters. And we'll end up with 0.0025 moles. So that's how many moles we're starting with HF, which means we have to add that many moles of OH minus. So let's say that this is, now we want 0.0025 moles of OH minus. And we know the concentration of OH minus is 0.1 moles per liter. Okay? So we divide by the concentration. We'll end up with 0.025 liters, or 25 mils. So we need to add 25 milliliters of sodium hydroxide in order to reach the equivalence point. Questions on that calculation? All right. So we know that our equivalence point is going to occur at 25 mils. We're going to keep that in mind because we know past the equivalence point, anything past 25 milliliters, we're going to work with strong base. That's the only thing that's going to affect the pH. And before that, we may have a buffer, unless we're very early on, haven't added any base at all. Yeah?
Wait, so how do you know it's 20.0025 moles? That's going to dissolve to H plus? Because HF is a weak acid, right?
Mm-hmm.
So shouldn't we find the H plus by doing like Ka equals that?
So the question is, why don't we worry about the Ka when we're looking at the volume at which the equivalence point occurs? And we don't have to worry about that here because we're doing a reaction. We don't have equilibrium, essentially. So this reaction we know is going to occur to completion until we have an excess of OH minus. And we've gone past that. Yeah, good question. Let's go back to our. Okay, so the first thing to do, and I think we actually did do this step, was to calculate the pH before any base is added. Yes. Sure. Okay. So here, when we're looking at the pH before any base is added, we haven't done any reaction yet. Now the only thing we have to worry about is our HF and its equilibrium in water. So here we have a weak acid problem, an ice table problem. Okay, you could set up the whole ice table. I'm going to skip down to the equilibrium line. Okay, I'm probably going to do that unless we get something incredibly complicated for the rest of titrations. So we'll have 0.1 molar HF. Some amount of that is going to react and form F minus. So there's going to be X moles per liter of F minus and X moles per liter of H3O plus. And so we can use our Ka and set up our equilibrium constant expression. We'll have X squared over 0.1 minus X. And in this case, we can't ignore X. Okay? Ka is 1.8 times 10 to the minus 4. you do the test, 0.1 divided by the Ka, the test will fail. So you need to use the quadratic formula. And for the sake of time, x is equal to 4.2 times 10 to the minus 3. And this is going to be equal to the concentration of H3O plus and F minus. We're really only concerned about the H3O plus because we're just asked for the pH. So the pH is going to be equal to, in this case, 2.38. Okay. Questions on that problem? Hopefully straightforward. This is midterm 2 type of problems here. Actually, all of these problems are midterm 2 type problems. That you just have to realize where you are on the titration curve. The titration curve type of problem is essentially just a buffer problem. So we're going to add 10 mils of sodium hydroxide. So you can just imagine you have a flask of weak acid, and you're going to add 10 mils of sodium hydroxide, force some of that reaction to occur, and now you want to know what the pH is that's left over. Okay. So in order to do this, we need a reaction table. So I'll set up my reaction. HF plus OH minus going to react to form F minus and H2O. And for our reaction table, you'll recall we need to use moles in the table. Yes?
If we didn't know the equation for formic acid, we just use HA.
Yeah, if you don't know the equation for an acid, feel free to use HA, for sure. I usually do that when I'm, for any weak acid, when I'm lazy. Okay. So we need to find the moles. So we start with 25 mils of 0.1 formic acid, multiply the molarity by the volume, and we'll get 0.0025 moles of HF. And we're adding 10 milliliters of 0.1 molar sodium hydroxide. So we're going to have 0.0010 moles of OH minus. Again, this is a limiting reagent problem, so we'll do minus 0.0010. And so we'll have 0.0015 for HF, 0 for OH minus, and 0.0010 for F minus. Questions on that? Right? We have both HF and F minus in solution. So we have a weak acid and its conjugate base. So we have a buffer. So we can use the Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA. If you're ever tired of looking up the Henderson-Hasselbalch equation and want a good way to remember it, pH equals pKa plus log of AHA. Helps. Okay. So you guys are really good today. Thanks. Okay, so our pKa is 3.74. We need some concentrations. A minus. We need a total volume. Okay, so let's start. Let's do total volume first. Okay, so we started with 25 mils of formic acid, and we're adding 10 mils of sodium hydroxide. So now in the flask we have a total of 35 milliliters of solution. So these moles of HF and F minus that we're calculating, those are all going to be divided by the 35 milliliters. And for A minus, I end up with 0.029. And for HA, I end up with 0.043. Skipping ahead there. Okay, so let's go back to our buffer equation. pH equals 3.74 plus log of 0.029 over 0.043. Okay, we have more acid in solution, so we should get a negative number here. Yeah. And pH is going to be equal to 3.57. Okay. Yes?
Since you're dividing both by, I knew you were going to since you're dividing both by volume,
Yeah.
the same volume, you can't say just
Yeah, because these are in the same volume, you can just ignore that. It cancels out in the equation. If you have a moles over a volume, and that volume's the same number, it does cancel out. But for some reason, I find that I always do this, and I think the reason goes back to when a case where it's something we talk about in the quantitative analysis course, where you can't use the Henderson-Hasselbalch equation. You need to use the concentration. You can't just use moles. So I'm just used to putting it in like this.
So like other instances where it's different volumes, or?
No, I don't think there can be a case of that, but it's just good habit, I think. Yeah. Okay, other questions? Yes?
So in the midterm, will there be any questions where we shouldn't use the Henderson-Hasselbalch?
No, different course. I mean, other than when it's not appropriate. Okay, other questions on that? pH has gone up, that's good, we've added base. Okay. Not too high, or before the equivalence point. Yeah, cool, good. All right. So pH at the equivalence point. We calculated earlier that this is going to be 25 milliliters of sodium hydroxide added. And so we do the same sort of thing. You can set up a reaction table, HA or HF plus OH minus, forming H2O and F minus. You should find that you end up with zeros on your reactant side, right? So anything that you started with moles of HF, that was 0.0025. We've now added 0.0025 moles of hydroxide. By definition, we're at the equivalence point, okay? So minus 0.0025 on the reactant side and plus 0.0025 on the product side for fluoride. Okay, so the only thing we're going to have in solution is F minus. Okay, so we've got moles of F minus. We're going to want concentration because we're going to use the equilibrium of F minus in water. And we're going to use an ice table. And because F minus is the conjugate base of the weak acid, we need to find Kb. We were given Ka, but we need Kb. I'm getting a little bit ahead of myself here. Oops. Okay, so first, let's go back. Let's find the concentration of F minus. What's our total volume? Yep, 50 mils, 0.05. Okay, so we'll use that in our ICE table. So we're going to have 0.05 minus x for F minus, x for HF, and x for OH minus. So we can set this equal to KB in our equilibrium constant expression. KB is going to be equal to 5.6 times 10 to the minus 11. Is that right? Yeah. That's a nice small number, which means we're going to be able to assume that x is small in comparison to the 0.05. Okay, and so when we calculate x, we'll get 1.7 times 10 to the minus 6. And this is equal to the OH minus concentration, right, because that's x. So our POH minus the log of that, we get 5.78. Converting to pH, 14 minus 5.78, we get 8.22. Okay, so our pH has gone up significantly, that's great. It's above 7, that's what we expect for the equivalence point of a weak acid, right? So those two things check out. Questions on that problem? Yeah? The other way to do it, you can kind of skip, once you understand what's happening, and you can actually skip this this reaction table, and know that the starting moles of HF is going to be what you end up with for F minus in this point here. Assuming it's 1-to-1, correct? Yeah, as long as it's monoprotic weak acid, and then you can just do the ICE table for the conjugate base. So it's a little bit of a make it easier for you. What else? Okay. Be one arrow.
Okay.
At the equilibrium that we just drew on the last slide, F minus plus H2O in equilibrium with HF plus OH minus. Okay. So what happens if you add excess OH minus to this reaction? It shifts towards the reactant side. So the formation of HF and OH minus is very small for this equilibrium. And that's why from the questions, what else? Yeah?
Why did we make an ice table if you just the last problem?
The last problem then is the pH 10 milliliters past the equivalence point. So this is an addition of 35 milliliters of base. Okay. Whoops. Oh, that's fun. Well, I did 1 milliliter in my notes. So. All right. You okay. Okay, so do this problem the same way essentially as the last problem. You set up a reaction table. And I'm going to go ahead and include my starting moles of HF. 0.0025, excuse me. And now we're adding 0.0035 moles of hydroxide, yes?
Has it always been one arrow, or like, when did it change to one arrow?
The reaction table should always be single arrow. And now our limiting reagent is HF. The important thing to note here, so we'll subtract out our 0.0025, and we'll get 0.0010. We do create F minus. But it's not going to play a large enough role in the pH that we're going to even worry about it, okay? F minus is produced, but we can ignore it. And the reason being is that if you look, you can ignore F minus here, because we're going to have so much excess OH minus that is not going to play a role. Does that make sense? So now the only thing we need to worry about is the concentration of OH minus. And right now we have moles, 0.0010. We have a total volume. We started with our 25 mils. We've added 35 mils. So we have 60 milliliters. So I have a concentration of 0.017. And now we can find the pOH by taking minus the log of that concentration. And I get 1.77 for my pOH. And so I get 12.23, 12.2, whatever. Yeah, 12.23 for my pH. All right, questions on that? Yes?
I was gonna say, I didn't use a reaction table for this,
Mhm.
because you know you use 25 milliliters, so you have 10 milliliters excess,
Mhm.
so I used to do, just multiply the excess by the molarity
Yep.
times.
That's a good point. So the other way that you can approach this problem without using a reaction table is you know that it took 25 milliliters of sodium hydroxide to reach the equivalence point. So you have an excess of 10 milliliters of hydroxide. So you can figure out the moles that are left over from that, directly from that volume, and then divide by the total volume, and so skipping that reaction table. Okay, yeah, either way works. Yes? Yes, you can always assume that the conjugate base, once you're past the equivalence point, is negligible. With the tiny caveat, and I've never seen anyone ask a problem where, what's the pH, 0.0001, you know, something stupid like that, yeah. Right beyond the equivalence point. And you could see that, so the last problem, not an ice table, it's a reaction table. And it's just my bookkeeping way of keeping track of what moles are going to be left over for the hydroxide. Oh, how come we didn't use it in part 4? Because the nice thing about, okay, we don't have to worry about F minus, okay, because it just is not going to have enough of an equilibrium and affect the pH at all. So we have OH minus, and one of the nice things about strong base is that you don't have to use an ice table. You can just take minus the log of its concentration. So you can avoid all of that. No, OH minus we definitely have to worry about. So that's what's giving rise to our pH. So this is what we had to do.
I meant the F minus.
Oh, yes. Yes, sorry. Yeah, F minus is negligible. Yeah. What else? Okay. All right. Let's do a weak base. So this is a figure that basically shows you the titration of a strong base with a strong acid. That's the dotted line. And then also a weak base titrated with a strong acid. Okay. The pH is less than 7 at the equivalence point. So let's say we have a base B, and we are reacting with H3O plus and forming BH plus, that's the conjugate acid, and water. Okay? If we've reached the equivalence point, that means we've gotten rid of all of our base because we've reacted it with the strong acid. So the only thing left in solution is BH plus. And so it's going to be in equilibrium with water and form the base plus H3O plus. And because we have the H3O plus, that means our pH is going to be less than 7, as long as we're at 25 degrees Celsius. Okay? That make sense? Yeah.
Are there any situations in which, like, you can't just skip to like the equilibrium?
For
Like, what's the purpose of like doing the BCA when like the majority of them turn out to be like ice?
yeah, so what's the point of doing the BCA table when mostly you end up doing equilibrium? It's bookkeeping, basically. It's a good idea just to keep track of where everything is. Once you know you're at an equivalence point, if you want to skip right to the moles, you know you should have, that's fine. But I like to do it just to keep my mind in check, just, keeping it all in order. And especially when you're in that, I mean, you need to do it when you're in the buffer region for sure. So, what else? Okay, so I'm going to have you guys work on a weak-based problem. I'm going to walk around, see how you're doing. These are essentially the same as the weak acid problem. We've got 4 different points, 0 mils of acid, of titrant added, 3 mils added, equivalence point, and then 15 mils added. Pretty straightforward.
Yeah, I'm just referring back to what I had. So we find the equivalence point like the same way?
Yeah.
They did. She did like switch out. I'm just trying to figure out like how she likes that. Yeah. It might be switch. Yeah, she kind of some of it. So we go years added.
I would say that
I think this is messed up so much, which is what's confusing me, but this makes more sense to me than this does. It's wording like spooky magically. So I'm just trying to figure out so let's
do it so that you're left with meters of X.
okay.
Is that what it was?
OH minus HA, polarity.
I think that's right. That might be right. Where are we at? Hang on. What'd you get?